Okay, let's start. Good morning, everyone. My name is Utkarsh Kushwaha, and I, with my three other teammates Rahul Dev Kumar Prajapati, and Rohit Pant, have developed a project on compiler design. Our project is basically an arithmetic expression evaluator. This project basically evaluates arithmetic expression and implements every phase of compiler to evaluate these expression. It basically this in this project we have tried to visualize how the compiler works at backend and how the different phases of the compiler work. What are the input of the different phases of the compiler? What is the output in every phase of the compiler? So that if a new student is trying to learn something trying to learn compiler design, he can easily visualize what are the different input and output for the different phases of the compiler and how the compiler actually works in the backend. In this project we have built in C++. We have implemented a recursive descent parser in this project, and to make the GUI, we have used GTKmm 4 library, which is a library in C++ that supports modern GUI. So let's run this project and test this for some given inputs. So let's run the project. This is a kind of window that you will come upon when the GUI is opened. This area here is the box where the expression input is given. This pink dev box is basically a area where the errors are shown. Errors such as sometimes user can give symbols as input which are not valid for an arithmetic expressions. These errors can be depicted here over here. Errors such as divide by zero errors is shown over this area, and this area is a notebook with different tabs that shows the phase output of different phases of the compiler, such as token, which shows the output of lexical analysis. That is this the output of lexical analysis is stream of tokens, and after that lexical analysis, taking that lexical analyzer as input, uh, syntax analysis is done, and the output of that syntax analysis is a parse tree. So AST is generated here, and then in this phase, steps how the AST is evaluated is depicted in the compiler in this step. This step shows the result. Uh, Three address code, symbol table, and graphs tab is here. Let's let's start with some basic input and check our result. So let's say suppose we give an input 2 into 3, 2 in 2 plus 3 into 4. Evaluate. So the first phase is tokenization. So the given input string is tokenized, and an AST is generated corresponding to that token. Now with the help of this AST, this equation will be evaluated. So this is the step that the compiler will follow to evaluate this expression. This tab shows the final result of this expression. That is, first of all, 4 into 3 will be evaluated, which is 12, and then plus 2 will be done. So final answer is 14. Here, three address code is generated. First of all, in T0, 3 into 4 is evaluated and stored, and then in T1, 2 plus 20 is done. Symbol table in this case is empty because symbol table is only generated when there are some variables used. And this is the AST graph that is generated. This is to visualize how actual AST is built in the background of the compiler. The work of this AST graph is this. Let's take some variables as input so that we can also test our symbol table. Let's suppose we give x is equals to 3, comma, y is equals to, let's say we give sine 45, comma, z is equals to x plus y. And when we click on evaluate, let's click on evaluate. The tokens are generated and the AST will be generated. Uh, After the AST, the steps of evaluation is generated. The sequence in which the compiler evaluates these expression and the final result, then the final result will be stored. Now here three address code is generated. Basically, first of all, x is equals to 3, then T1 calls for sine 45, and the final result is stored in Z, which is also depicted in our symbol table. Symbol table is basically in our symbol table basically is a table or a data structure where in the input variable, what is the value corresponding to it is stored. And in symbol table, type of that values are also stored. This is the AST graph corresponding to this equation. Let's test some other functionalities, other functional support that we have done in this compiler, such as suppose we have to calculate log 2 at base 10. So log 2 at base 10, our base is 10 and we want to evaluate log 2. Let's click on evaluate and see what is the result. This will are the this is our AST generated. This is the step that compiler will follow. The final result and the three address code corresponding to this and the AST graph. Let's take some other inputs. So we have support for functions like tan. So let's give tan 90. What will be the output of tan 90? Let's see. The result of the tan 90 is 1.192. The point here is we are taking the values in radian, not in degrees. For the functions like sine, tan, cos, the values are taken in radians. Let's let's evaluate some other functions such as power function. So in our day-to-day life, we use power function as raised to the power. So here in our compiler also we have implemented this thing. Suppose we want to uh, take 2 raised to the power 3, and when we click on evaluate, the output is 8. The tokens are generated. The AST is built according to this. The steps will be generated. 3 address code. This is our 3 address code, and this is the AST graph, how the actual tree will be built. Let's say we want to compute 2 raised to the power 3 raised to the power 2. Here, as the associativity of the power function we have used is from left to right. So first of all, 3 raised to the power 2 will be evaluated, then the output will be raised to the power of 2. This is how this will be evaluated. And all other variables, all other operators that we have used have associativity right to left to right, but the power function is the only function which has associativity left right to left, not the power function. And the assignment operator also that we have used also has associativity right to left. Let's We have also the support for comparison operators. Let's test them. Suppose we want to check 2 3 is greater than 2 or not, and we will say in this case result should be 1 because 3 is greater than 1 2. So our result is 1. This is the corresponding AST, and the 3 address code generated will be this. Let's see if we write 3 not equals to 2. Now the result should be now the result should be 1. Let's see, the result is still 1. And if we say 3 is equals to 2, 3 is equals to 2, see, here it gives error. Why this error is corresponding? Because there is no such operators where two numbers can be equated. The operator here for comparison is double equals to. Let's type double equals to and check. So the result is 0 because 3 is not equals to 2. This error window also gives us errors such as 2 divided by 0. Let's evaluate it. See, it gives division by 0 error. And we have also implemented code optimization. For code optimization, we have removed identities from our equations. So let's give some input which has identities and try to remove it. Let's give an input. Suppose we give plus 0 plus 4 into 3 into 1 plus 4 minus 0. Let's uh, see here in this case, there are three identities: 3 plus 0, 3 into 1, and 4 minus 0. These should be removed before construction of our AST and evaluation. Then evaluation should be done. Let's check this. Let's click on evaluate. As we click on evaluate, in our AST, we can clearly see that the identities are removed. And after removal of these identities, our compiler will evaluate this expression, and this will be the graph, AST graph, that is generated for this expression. Uh, that's all in our project. Thank you very much.